Hey everyone. Up to this point in your calculus career, essentially everything you've done has been two-dimensional calculus, right? Studying curves on the plane, integration, all of that, excuse me, everything you've done has occurred in the plane. And now it's time to step up things one dimension, right? So far, here's what you've studied is the plane, which is often written as R2, and that's the set of all ordered pairs of the form x comma y, where both x and y are real numbers, right? So this is the set theoretic way to write the plane, right? And in the picture looks like this. There's an x-axis, there's a y-axis, right? And so a typical point in the plane, I'll write it as a comma b, right? That's a particular choice of x and a particular choice of y, right? So that's the plane. And what we want to do is take this up one dimension. And so we're going to study three-dimensional space. Which is typically written as R3. So that's going to be the set of all ordered triples, x comma y comma z, where x, y, and z are real numbers. So the R, that stands for the real numbers part, and then the 3, right, that stands for the dimension, so it's three-dimensional. Oftentimes, the set of real numbers is denoted by that symbol right there. So another way to write this, it's the set of all x, y, z, such that x, y, and z are in, and then I can use this symbol right here, right, the real number symbol. So each of x, y, and z are real numbers. The picture of three-dimensional space, well, okay, it's going to be kind of hard to draw on a two-dimensional object, right? So we got to somehow come up with a way to give depth. And so here's the way we do it. What we want to do now, there's going to be an x-axis, a y-axis, and a z-axis. And the standard for this is to draw the y-axis now as the horizontal axis, the z-axis as the vertical axis, and then you want to imagine the x-axis is coming straight out of the plane. To draw that on a flat board or on a piece of paper is like that. All right, but the way we want to think of this, the z-axis is coming straight out. This is done to obey what's called the right-hand rule. We'll talk a little bit more about the right-hand rule later on. But the right-hand rule goes like this. If you point in the direction of the positive x-axis and curl your fingers in the direction of the positive y-axis, your thumb will then tell you the direction of the z-axis. Right? We'll make use of the right-hand rule a little bit later on, but if you're reading the text, it'll say something like, the convention that we choose obeys the right-hand rule. Okay, so this is called the, this is the three-dimensional, I guess I want to put it down here. So this is the three-dimensional rectangular coordinate system. So when you hear the words rectangular, that's when you study three-dimensional space using x, y, and z. Coordinate system. Okay, so now if you want to talk about a point in space, it's going to be something of the form A, B, C. And so the way you do that, if you want to depict how it happens, right, you go out A units along the x-axis, you go over B units on the y-axis, and then you go up C units along the z-axis, and so that point right there is A, B, C. Where there is the position C. All right, it's a little bit tough, and you don't have to be a great artist. I'm definitely not a great three-dimensional artist. That's not what this class is about. All right, we want to be able to do the mathematics behind 3 dimensions, but that does not require that you're a great three-dimensional artist. So in the plane, right, so in R2, an equation involving the 2 variables, so involving x and y, describes a curve, right? We've done lots of this studying of curves, right? So for example, if you have x squared plus y squared equals 1, right? Here's an equation involving the 2 variables, and what do we get? We get a curve. In this case, it's a circle. So now we want to take this up 1 dimension. So in R3, an equation involving the variables x, y, and z describes what's called a surface. Now, surfaces can get very complicated very quickly, right? So we want to just sort of get a good understanding of fairly simple surfaces, right? But they will show up in this class, and especially those will become important in Math 241. Now, so what I'm going to do, I want to do an example, but I remembered one thing that I wanted to talk about coming back to this picture. So if you remember, you don't need to draw this. When you're working in the plane, there are 4 quadrants, right? First quadrant, second quadrant, third quadrant, fourth quadrant, right? So the axes divide our plane into 4 pieces, and those pieces are called quadrants. Now, we can do a similar thing with our 3-dimensional coordinate system. Now what it does, if you look at, and so let me say this, maybe I'll start the example now. So, okay. So there are now 3 different what are called coordinate planes, right? So so the planes, these are our first examples of surfaces. So the planes defined by, so the first one, let's do so part A of this is going to be, let's do z equals 0. This is called a coordinate plane, and this one is known as the xy plane. So remember, you're supposed to think of the x-axis is coming out of the board, and so if we take the equation z equals 0, what we're saying is we don't care what x is, we don't care what y is, but we are forcing z to be 0. And so what you get then is the plane that would be slicing right out of the board like this, right, horizontally, where the x-coordinate and the y-coordinate can be whatever they want, but the z-coordinate has to be 0, right? So this is known as the xy plane, right? It's the plane that contains the x-axis and the y-axis. B, if we require y equal to 0, this is known as the xz plane. So the x-axis is coming out of the board. The xz plane then would slice straight into the board vertically, right? And it divide this office, this room, into 2 halves, that half and this half over here. And then there's also the x equals 0. This is known obviously as the yz plane. And which one would that be? Well, now we're requiring x to be equal to 0, where y and z can be whatever they want. That would be the plane that is actually the chalkboard itself. Right? So those are known as the coordinate planes. Now, just as I was drawing that picture of how the x-axis and the y-axis divide the plane up into 4 pieces that we call quadrants, the coordinate planes chop 3-dimensional space into 8 pieces known as octants. All right, so the coordinate planes divide R3 into 8 octants. Now, it's not going to be important to know which one first, second, third, fourth, other than the first, right? You should know who the first octant is, and then I don't even know who the second, third, fourth, and the other octants are. So the first octant is the one where all the coordinates are positive or greater than or equal to 0, right? So the first octant so the set of all x, y, z in R3 where x, y, and z are all greater than or equal to 0 is the first octant. So what does that mean then? Well, if x has to be positive, that means that it's going to be in front of the chalkboard. If y has to be positive, it's going to be to the right of the xz plane. And then if z has to be positive, that means it's above the xy plane. Right, so that one's called the first octant. Now, we're talking about surfaces. These are my first examples of surfaces, right? The coordinate planes, but we can make things a little more complicated. So let's look at this example. Let's describe the following surfaces. And when I say describe, I may draw a picture or I may just use words to describe each one of these. So you just want to understand what's going on with these pictures here. So let's say part A. So remember, a surface is one that's described or that arises as an equation involving the variables x, y, and z. Now, if you have an equation and you don't see one of the variables sitting there, that just means there's no restriction on it. So this is an equation involving the 3 variables x, y, and z. But since we don't see x or y appearing in it, that means that x and y can be whatever they want, but we require z equal to 4. So what is that? Well, that's a plane, horizontal plane at height 4. Right, so horizontal plane at height 4. Next one, let's do this one. X squared plus y squared equals 4. Now, if you saw this equation and you're working in the plane, you say, oh, I know what this is. This is a circle of radius 2 centered at the origin. But now we have to remember that we're working in R3. So this is a surface. And what this means is we don't care what the z-axis or what the z-coordinate is. But the x and y coordinates have to satisfy this equation. Which means then, at any choice z, no matter what z is, the x and the y coordinates have to lie in a circle. And so what we get is what's known, I'm going to draw the picture, and so this is known as a cylinder, and you can draw it like this. All right, so the z-axis is going to be coming right, or going right through the middle. The y-axis is like this, z-axis comes out, both front and back, and then, so who is this point right here? When it crosses through, there's a circle. Okay, so that's at point 2, that's at 2 right there. Right, so this is a cylinder of radius 2. It goes up forever, it goes down forever. So cylinder of radius 2. We know how to measure distance in R2. Now we want to generalize this formula for distance in R3. So if, let's say x1, y1, z1, and x2, comma y2, comma z2 are in R3, right? So now we've got a couple of points in three-dimensional space. Whoops, R up or 3. The distance between them and this distance formula is going to look just like or very close to the two-dimensional distance formula. So the distance between them is, so we're going to have a big square root and then it will be subtract the x coordinates, x2 minus x1 squared, subtract the y coordinates, y2 minus y1 squared, and subtract the z coordinates, z2 minus z1 squared. Subtract the coordinates, square the results, add those together, take the square root. There's the distance formula. Now this leads to an important surface, right? This distance formula. So let's define what we want to talk about a sphere. So definition, a sphere of radius, say r, with center A, comma B, comma C, is the set of all points in R3 that are distance, so distance R from the center, so from A, comma B, comma C, right? So that's what a sphere is, right? Pick a central point, and then all the points that are a fixed distance R from that center, right? That's called a sphere. That's how we'll draw a sphere on the board. Right, so that distance is R. Right, so there's a typical drawing of a sphere. Now, using this definition combined with our distance formula is going to allow us to find a formula or an equation that describes the sphere. So let's see if we want the distance from any point on the sphere. So here's a generic point, x, y, z, sitting on the sphere. We need that distance right there to be r. So we need the distance from x, y, z to a, b, c to be equal to r. So how would we measure that? Well, it's going to be square root of x minus a squared plus y minus b squared plus z minus c squared. That has to equal to r, and square roots make things ugly. And so what we typically do is square both sides. And so the standard equation of the sphere centered at ABC with radius r is x minus a squared plus y minus b squared plus z minus c squared equals r squared. So there is the standard equation standard equation of a sphere. Okay, so now let's try some examples involving the equation of a sphere. So the first one, let's look at this one. X minus 1 quantity squared plus y minus 1 quantity squared plus z squared equals 1. What we have here is, so the radius is 1, and the center, right, we can just read this off. This is going to be a center of 1, comma 1, comma 0. another example. And sometimes we'll be interested in regions rather than actual surfaces. So this one right here, 1 less than or equal to x squared plus y squared plus z squared less than or equal to 4. Okay, so we want all points x comma y comma z that satisfy this inequality right here. So if you look at the first half, what we need are points that lie outside the sphere of radius 1 centered at the origin. And then if you look at the second half, inside the sphere of radius 2 centered at the origin. So you can kind of draw a picture here. Let's see if I can do this. Oh, you know what? Let me do it with dotted lines here. So we've got sort of concentric spheres. The inner sphere, the outer sphere. Sorry, that's kind of an ugly picture there, but that's the idea, is you've got a sphere inside a sphere, and we want all the stuff in between the two spheres, including the outer and inner spheres. And I should point out, I'm really not a very good three-dimensional artist. I definitely don't expect you to be great three-dimensional artists either. So let's do a couple more examples here. So let's describe the region, or let's describe the region using equations. All right, so I'm going to describe it in words, and then we want to actually write down the equation. So the first one, the plane perpendicular to the x-axis through the point 1, 0, 0. And then the second one, let me write them both down and then we can do them. So the second one is the circle the circle of radius 3 lying in the xy plane. So the circle lying in the xy plane centered at 0, 0, 0 with radius 3. All right, so the first one, we want the plane perpendicular to the x-axis. All right, so let's draw an xy plane, or a yz plane here, and then the x-axis is coming straight out. We want it to be perpendicular to the x-axis, so it needs to be parallel to this chalkboard here, and then passing through the point 1, 0. Well, so what that says is then we don't care what x is. We don't care what y is. We don't care what z is, but we require x to be equal to 1. And so this one, it's just the plane x equals 1. For the second one, we want the circle lying in the xy plane centered at this point, 0, 0, 0, origin, with a radius 3. Well, okay. A circle with radius 3 looks like that, right? In the xy plane. However, we have to remember that we are working in three-dimensional space. And so when we write this, what we really get is a cylinder, unless we say additionally that we require z equal to 0. Now we're lying in the xy plane, so rather than the entire cylinder, right, we just get this portion right there. So it requires two equations to actually describe that. Okay, so that's sort of an introduction to three-dimensional space. We're going to stop here, and we will see you next time, okay?